Hey, Physics 20s, it's Mr. Jukely here. Guess what? We are on Unit 6, and we're obviously on Lesson 1 here of Unit 6, but this is really exciting because this is our last unit in Physics 20. We're so close to being done Physics 20, which is really cool, really exciting. So good work, stay strong, Physics 20s. We are almost there. So yeah, let's jump right in. This video is going to focus on the wave side of things. The first part of this unit talks about simple harmonic motion and stuff like that. We'll discuss more in Google Classroom, but we're focusing on the wave part for this particular video. So first and foremost, a wave, when we talk about a wave, it's a transfer of energy from a source to a receiver, not matter, right? So that is, in other words, it's kind of like a traveling disturbance through a medium. So we got to talk about all these different little pieces here. So until now, we have talked about transfers of matter. So like person number one throws a football. It goes into this nice parabolic motion, and we have this 2D projectile. It is the matter, the football, that's traveling from one location to another. What we want to talk is not matter really traveling, we want to talk about energy traveling. So a good thing to consider with this is just a set of dominoes, and I'm sure most of us have played with dominoes before. So you hit one domino, it runs into the next one, then runs into the next one, then runs into the next one, which is fine. But you see, do the dominoes really move? Not really, right? So what we look at with this is, well, I can apply a force to that first domino. Here's my force being applied to that first domino. It's going to make it move a particular distance, and we know that force times distance is work. So essentially, I'm doing work. We know that work is a change in energy. So by doing work, by applying that force and make it move, I've changed that domino's energy. Right, so now it's going to be moving, it's going to be falling over. This is kind of going to be called our source vibration, is the little flick that you give the domino. It's where it all starts off with. So we flick that domino forward, it gains some kinetic energy, and it falls over, and then it hits the next domino. What does it do to the next domino? Well, it applies a force, and that force makes the next domino move a distance, so it changes the energy of the next one. Then that energy gets transferred to the next one, and then to the next one, and then to the next one, and so on, and so on, and so on. So notice how it is the energy that has moved. Did the dominoes really go anywhere? I mean, they fell over, but they didn't really go anywhere. So it's just sort of like a disturbance. And this is the big idea of a wave, right? It's the disturbance through a medium. A medium is the stuff that the wave travels through, that allows that energy to travel from one place to another. So if you want to see a video on this, just look up, like, and there's so much of this on the internet. This one's a pool player or billiards player with dominoes on it. Just look up domino tricks or something like that on YouTube. You'll find all kinds of crazy stuff with this. Okay, so getting into a little bit more specifics here, there are two types of waves. There are mechanical waves. Mechanical waves must travel through matter. So in other words, they have to travel through an actual medium. They have to travel through stuff. So for example, a spring, the wave travels through a spring. This always reminds me of when I was younger, my parents had an electric lawnmower. Here's an electric lawnmower, and there's the cord, and you'd always have to like flick the cord, and when you flick the cord, you can get this one wave that travels through the cord. But anyways, that's if you've got an electric lawnmower, you know what I'm talking about. Sound waves travel through air. Water waves travel through water, obviously, but they have to travel through something. So for Physics 20, we're going to focus primarily on mechanical waves. Physics 30 is all about electromagnetic waves, or EMR, which you know primarily as visible light, but realistically there's tons of different types that are all kind of the same thing. Anywhere from radio waves all the way up to gamma rays, they're all EMR. Thing about this is, and about these electromagnetic waves, is they do not need a medium. They do not need a medium. And I mean, there's a ton of other things too. Like half of Physics 20 is about electromagnetic, or sorry, half of Physics 30 is about electromagnetic radiation. But But yeah, for now, just know that you don't really need a medium for it. So one thing to note, vibrations are the source of all waves. So for example, if I wanted to have, and actually let me just switch this up to, oh no, not what I want to do at all there. Where is it? Where is it? There it is. If I want to switch this up to the thing where the animations actually work, pretend that we have a guitar string. So here's a guitar string. What do you need to do in order to make that guitar string vibrate? Well, you need to pluck it. So you need to make it go back, and then it'll spring back to its original place, and it'll spring back and forth. And then down here we can see it's making those waves. Those are actually compression waves that we'll talk about, or longitudinal waves. We'll talk about those definitions a little bit later. But the string vibrating back and forth causes the air to vibrate back and forth around it, which causes our actual wave. Pretty neat, right? And you can think about all kinds of different things that do this with sound. Sound's a huge part of our Physics 20. Oh, discard those. Go back to the thing that I can actually write on. Like your voice box even, right? If you grab onto your throat and you make some different noises, ooh versus ooh, you can feel your voice box not only vibrating, but vibrating differently, and that's what's causing those sound waves. Cool. So our source vibration does a couple really important things for us. It provides our initial energy. So the more energy you put into the wave in the start, the more that's going to be transferred through the medium. And that kind of makes sense, right? Again, you can think about flicking your cord. You give it a little flick, you get a little wave traveling through. You give it a big flip. So this is your extension cord. You can go outside and try this with an extension cord or even a piece of rope as well. You just flick it and you can see the wave traveling down it. It also tells us about the frequency. Now frequency, this is something we kind of talked about before, but frequency is the number of cycles of the wave per second. So how many times the wave cycles or repeats itself in every single second. So the vibration that we look at, the initial source vibration tells us the frequency, so how quickly it is vibrating back and forth. And then something that we need to note, the frequency is the same. So the frequency of the source is the same as the frequency of the wave. That's something. And then something that's really, really important for us is the frequency of the wave never changes after it leaves the source. That being said, I can make a really high-pitched note, ooh, or a really low-pitched note, ooh, and they have very different frequencies. And you can even feel those frequencies when you grab your voice box. So high pitch is vibrating very quickly. That's a lot of cycles per second, whereas low pitch, less cycles per second. But so I can change it, but after it leaves my voice, it does not change. So this is true if there's friction, which, you know, energy takes energy out of the wave. If there's a change in the medium, which we'll learn later, changes the speed of the wave. If it bounces off a wall, which is reflection, like pretty much no matter what, the frequency of a wave does not change. The one sort of exception of that is the Doppler effect, which we'll talk a little bit more about right at the end of this unit. Cool. So again, reflection. When a wave comes in and it bounces off, frequency stays the same. So 60 hertz, which by the way, hertz is our unit for Hz, is our unit for frequency, and 1 hertz means 1 cycle per second, 2 hertz means 2 cycles per second, and so on and so on. So it's the number of cycles per second. Cool. This is the idea. This is actually called damping. So one thing that we're going to know with this as we go through is the amplitude. So amplitude is how big these crests and troughs are. We're doing a lot of definitions all at once here. So crests are above our equilibrium position, so I'm even going to label that equilibrium position. Troughs are below our equilibrium position. Remember, equilibrium position is, it's really easy if you think about this with a piece of rope. So a piece of rope might like to hang out like this, but you might have a wave going through that rope that looks kind of like this. The amplitude is how far away from that equilibrium position or how far away from that rest position it actually is. It typically talks about our energy. Amplitude talks about energy or represents energy. Might as well write out the whole thing. Cool. So this looks like we're losing amplitude, which means we're losing energy. You can think about with this voice again, right? If I sing my best A note, ooh, by the way, I have no idea if that's an A note or not, but ooh, and you've got that going through your speakers, that's fantastic. When you're really close to your speakers, you're going to hear that really loud. But if you go further and further and further and further away, it's going to get quieter and quieter and quieter and quieter because it's losing energy to its environment. Again, that is known as damping, when a wave loses energy. So this is the idea that when waves go from one medium to another, this is actually called refraction, and it's a big part of physics 30. We know it in physics 20, but a big part of physics 30. Refraction is when a wave changes directions because it changes speed as it goes from one medium to another. The frequency in all of these situations, though, notice does not change. If it's 40 hertz to start, it's 40 hertz to finish. If it's 100 hertz to start, it's 100 hertz or 100 cycles per second to finish. Cool. So next thing to talk about here is periodic motion. Periodic motion is motion that repeats itself over and over and over and over and over again. And we can already start to see with this spring that would be bouncing up and down, we can already start to see how this is going to kind of look like and kind of be represented by a wave. So again, we've got our equilibrium position. That's where if I had this little mass hanging from a spring, that's where it would like to go. If I were to pull that down, it would start to bounce and vibrate up and down and up and down and up and down. Picture hanging a spring for a thing, and the amount of energy or the amplitude is how far, again, from that equilibrium position. So we're already starting to see lots of similarities between this and waves. Another one that we could look at is a pendulum swinging back and forth. So as this swings back and forth and back and forth and back and forth, one cycle would be all the way there and all the way back. So from its starting position and through every position, I didn't actually mention with this one as well, but through its starting position, let's clean it up a little bit, from its starting position, all the way down to the bottom, all the way up to the top, and then back to its starting position. So from the start, through every position, and then back is one cycle. Could do the same thing with this, from the start, through every single position, and then back to the original spot is one cycle of the wave. Okay, so when we talk about frequency and period, we've already mentioned period before, right? Period is capital T. It's the time per cycle. You can find a formula on your data sheet for this. It's just the total time divided by the total number of cycles. So a very, very particular amount of time. It's the time per cycle. Frequency is the exact inverse of that. So when we check out the frequency formula, it's the total number of cycles divided by the total time, or in other words, it's the cycles per unit time, or the cycles for us, it's going to be the cycles per second. And again, it's measured in hertz, where 1 hertz is equal to 1 cycle per second, 2 hertz is 2 cycles per second. Now, if you've already noticed that these two things are, I'll go back to that one. If you've already noticed that period and frequency are an inverse of each other, you are spot on. They are so closely related and they're so easy to go back and forth from one to the other. I'll give you a formula for that in a second. So let's just look at something here. A piano chord is vibrating at 1024 hertz. What that means is it's 1024 cycles in 1 second, so 1024 vibrations. An FM radio station is set at 96 megahertz. That means it's creating 96 million cycles of its wave every single second. So hertz is the number of cycles per second. Okay, period, we already kind of talked about this one, right? So if I have a period of 2.5, that means it takes 2.5 seconds to make 1 cycle. Cool. Okay, and again, this formula is just on our data sheet. Something you need to know also on our data sheet technically is that they are inverse of each other or reciprocals of each other, period and frequency. So let's say that I had a frequency equal to 2 hertz. Let's just think about this for a split second. 2 hertz, that means 2 cycles in 1 second. 2 cycles in 1 second. So how long does 1 cycle take? Well, it's 2 in 1 second. It should take half a second. Now, if we wanted to look at this in our calculator, we wanted to look at the actual formula for this. Let me get out the old calculator here. So I am given the frequency and I'm looking for the period. All I do is 1 divided by the frequency, so 1 divided by 2. There is, I got too much going on up there. 1 divided by 2, there's my period. 0.5 seconds for 1 cycle. If I wanted to go back and I wanted to figure out the frequency, I do 1 divided by 0.5, so 1 divided by my period, and it gives me 2. So it's really, really easy. There's even a button for this. So inverse of the answer is 0.5, inverse of the answer, no, that's squared. Inverse of the answer, so that's right above the squared button, which is why I made that mistake in the first place, is equal to 2. So if you do to the power of -1, or you do 1 divided by whatever your frequency or period is, it will give you the other thing. It's so simple. So simple. Okay, so last thing, maybe just put this on pause and see what you picked up on. Go ahead and do that right now. Answer these couple or fill in the blanks for these couple of questions. All right, so if you answered a wave is a transfer of energy, perfect, you picked up on things. The material a wave travels through, well, that's called the medium. So waves travel through a medium. Well, some waves travel through a medium, which leads us to the next thing. There are 2 types of waves, electromagnetic and mechanical. And again, it's those mechanical ones that need the medium. The source of all waves are vibrations. Vibrations, excellent, most excellent, perfect. So a bit of review there. Couple more for you to think about. So again, when you're ready, put the video on pause and unpause when you think you've got it. So I'll let you go ahead and do that right now. Go for it, put the video on pause, see if you can figure out these last couple questions. Alrighty, so the source vibration does 2 things. It tells us about the initial energy, and it also tells us about the frequency of the wave. Which property of a wave never changes? Frequency never changes. Again, that's after it leaves the source. What does it mean when something vibrates at 40 hertz? That's 40 cycles in 1 second. Awesome. And then what does it mean when it has a period of 0.7 seconds? That means it takes 0.7 seconds to complete 1 cycle. Complete 1 cycle. Awesome. So if you got those things, you're honestly probably good to go for this particular video and this particular lesson. It's getting our feet under us. The simple harmonic motion stuff, this is something for this, the whole corona piece that we're probably going to skip over for the sake of time. It doesn't really show up in Physics 30 very much. But if you want to check it out, absolutely go for it. It's actually going to be this. I better check the calendar here. This little section that we're going to skip over, and then we're skipping right to lesson 5. So the universal wave equation and wave types. So all of this simple harmonic motion stuff is bonus material for you. Again, if you want to check it out, awesome, go for it. If not, oh, that's okay too. Do what you can. Okay, anyways, Physics 20s, it's been fantastic talking to you again. We'll see you again soon. Bye for now.